Deep in Earth's ancient past, a single landmass dominated the planet, Pangea. This is the story of a world unlike anything we see today, when nearly all continents were locked together in one immense supercontinent. For hundreds of millions of years, Earth's surface was reshaped by slow-moving tectonic forces that welded and later tore apart this giant land. Oceans shifted, climates transformed, and life adapted across vast interior regions far from modern coastlines. As time passed, Pangea began to break apart, setting the stage for the continents we recognize today. Its legacy remains written in geology, fossils, and the continuing movement of Earth's plates beneath our feet. Pangea Formation describes a long geological process during which many earlier continental fragments moved across the surface of the Earth and eventually joined into one large, continuous landmass. This process took place over a very long span of Earth's history and involved repeated cycles of breaking apart and joining together of crustal pieces. The formation did not happen suddenly, but through continuous movement driven by the slow motion of Earth's outer rocky layer, known as the lithosphere, which is divided into multiple plates that move over the softer layer beneath it, called the asthenosphere. The Earth's outer surface is made of several large and small plates that carry continents and ocean floors. These plates are always in motion, although the movement is extremely slow on a human timescale. Over millions of years, this movement causes continents to drift, collide, separate, and reshape the surface of the planet. During earlier periods in Earth's history, before Pangea formed, the continental crust was already broken into several major landmasses and many smaller fragments. These fragments were not fixed in place. They moved independently across the globe due to internal forces within the Earth. The origin of these movements is connected to heat inside the planet. Heat from radioactive decay and leftover energy from Earth's formation causes slow movement in the mantle. This movement creates convection currents that circulate material inside the Earth. These currents transfer energy upward and influence the motion of the lithospheric plates above. As the plates move, they interact at their edges. At some edges, plates move apart. At other edges, they move toward each other. At other edges, they slide past one another. The interactions at converging boundaries played a central role in the formation of Pangea. Before the full assembly of Pangea, the Earth's landmasses were organized into earlier supercontinents and fragmented continents that changed position over time. One of the important earlier landmasses was Gondwana, which included many of the southern continental fragments. Another was Laurentia, which formed part of the ancient northern landmasses. There were also other fragments such as Baltica and Siberia. These landmasses were separated by ancient oceans that no longer exist today. Over time, the movement of tectonic plates caused these landmasses to move toward each other. When two continental plates moved toward each other, the ocean floor between them was gradually consumed into the mantle through a process called subduction. Subduction occurs when one plate bends and moves underneath another plate into the deeper layers of the Earth. This process reduces the size of ocean basins and brings continents closer together. As subduction continued for millions of years, ocean basins between continental fragments became narrower. The edges of continents began to interact more frequently. These interactions caused deformation of the crust, leading to the formation of mountain belts at the zones of collision. When continental crust collides with continental crust, neither side easily sinks into the mantle because continental crust is relatively buoyant. Instead, the crust is compressed, folded and thickened. This thickening of crust contributed to the development of large mountain systems during the assembly process. The movement of Gondwana toward northern landmasses played an important role in the formation of Pangea. As Gondwana moved, it approached smaller land fragments and larger continents. At different times, parts of Gondwana collided with other landmasses, causing changes in the arrangement of continents. These collisions were not single events, but occurred in stages over long periods of time. Each stage contributed to the gradual reduction of ocean spaces between the continents. The closing of ancient oceans was a key part of the formation process. One of the important ancient oceans was the Iapetus Ocean. This ocean separated major landmasses before their collision. As tectonic plates moved, subduction zones consumed the oceanic crust of the Iapetus Ocean. Over time, the ocean became narrower until it fully disappeared as continental collisions completed its closure. Similar processes occurred with other ancient ocean basins that existed between different continental fragments. The collision of Laurentia with other landmasses contributed to the assembly of larger continental structures. Laurentia experienced interactions along its edges that led to deformation and mountain building. These processes were part of repeated cycles of collision and separation that occurred in earlier geological periods. As Laurentia moved, it gradually became integrated into larger continental assemblies through tectonic activity. Baltica also played a role in the formation process. It moved across ancient oceans and eventually collided with other continental fragments. These movements were guided by the continuous motion of tectonic plates driven by mantle convection. The collision between basaltite and other landmasses caused the formation of mountain belts and contributed to the reduction of oceanic areas between continents. Siberia was another major continental fragment that participated in the formation process. It moved through ancient oceanic regions and eventually came into contact with other land masses. The interactions between Siberia and neighboring continents contributed to crustal deformation and the formation of structural features that remain visible in geological records today. As these continental fragments moved and collided, the structure of the Earth's surface became increasingly organized into larger connected regions of land. The accumulation of collisions led to the gradual formation of a continuous landmass. The final stages of assembly involved the joining of major continental blocks into one extensive supercontinent. The process that led to the formation of Pangea involved repeated cycles of opening and closing of ocean basins. These cycles are part of what is known as the supercontinent cycle. In this cycle, continents break apart, drift, and later recombine into larger landmasses. The formation of Pangea represents one complete phase of this cycle, where dispersed continents eventually join together into a single large structure. During the time leading up to Pangea, the Earth's surface experienced significant tectonic activity. The movement of plates was not uniform but varied in direction and speed depending on the forces acting on them. Some regions experienced strong compression, where continents collided. Other regions experienced extension, where crust was pulled apart. These variations contributed to the complex arrangement of landmasses before final assembly. The closure of ocean basins was not a simple process. Oceanic crust was continuously formed at mid-ocean ridges, where magma rises from the mantle and solidifies to create new crust. At the same time, older oceanic crust was destroyed at subduction zones. The balance between creation and destruction of oceanic crust determined the size and shape of ocean basins. During the formation of Pangea, destruction at subduction zones exceeded creation in many regions, leading to shrinking oceans. As continents approached each other, sediment that had accumulated on ocean floors and continental margins was compressed. These sediments were folded and uplifted, forming thick layers of rock. These rock formations became part of mountain belts that marked the zones where continents collided. The growth of these mountain belts reflected the ongoing convergence of tectonic plates. Heat and pressure during collisions caused changes in rocks. Rocks were transformed into different types through metamorphic processes. Minerals within the rocks were rearranged due to intense conditions deep within the crust. These changes contributed to the formation of complex geological structures that are still present in ancient mountain regions today. The formation of Pangea also influenced the distribution of volcanic activity. Subduction zones produced volcanic arcs, where magma rose through the crust. These volcanic regions formed chains of volcanoes along continental margins and island arcs. As continents moved closer, some volcanic arcs became part of continental landmasses, adding new crustal material to the growing supercontinent. The movement of tectonic plates that led to Pangea was guided by long-term forces within the Earth. Slab pull played a role in driving plates into subduction zones where dense oceanic crust sank into the mantle. Ridge push also contributed to the movement of plates away from mid-ocean ridges. These forces worked together over long periods, shaping the movement of continents. As more continental fragments joined together, the arrangement of Earth's surface became increasingly concentrated into a single landmass. The final assembly involved the joining of multiple continental regions along zones of collision. These zones became marked by extensive mountain ranges and complex geological structures. The interior of the forming supercontinent experienced changes as well. As landmasses merged, large areas became far from oceanic influence. This affected erosion patterns, sediment distribution, and long-term geological stability. Rivers and inland basins developed across the interior regions of the growing supercontinent, carrying sediments from highland areas toward lower regions. The assembly process also influenced the configuration of surrounding ocean basins. As continents joined, remaining ocean spaces were redistributed around the edges of the supercontinent. Ocean circulation patterns changed as the shape of the global land distribution evolved. The formation of Pangea involved the integration of crust that had formed at different times in Earth's history. Some crustal regions were very old, having formed in earlier geological periods. Other regions were younger and had formed closer to the time of assembly. The combination of these crustal regions created a complex structure with varied geological histories. As collisions continued, faults developed within continental regions. Faults are fractures in the Earth's crust where movement has occurred. These structures accommodated stress caused by the convergence of plates. Some faults formed deep within the crust, while others extended closer to the surface. The development of faults contributed to the overall structural complexity of the forming supercontinent. Magmatic activity occurred in various regions during the formation process. Magma generated in the mantle rose into the crust and formed intrusive rock bodies. These bodies cooled slowly beneath the surface, forming large crystalline structures. Some magma reached the surface through volcanic activity, creating lava flows and volcanic deposits that became part of the continental crust. The assembly of continental fragments also affected the thickness of the crust. Where continents collided, the crust became thicker due to compression and stacking of rock layers. This thickened crust formed elevated regions that influenced surface processes such as erosion and sediment transport. Throughout the formation process, the Earth's surface was continuously reshaped by tectonic forces. These forces acted over extremely long periods. The geological processes that led to continental collision began deep within the Earth, where heat and pressure created continuous movement in the mantle. This movement was slow but constant over very long periods of time. The outer layer of the Earth, known as the lithosphere, was broken into large and small sections called tectonic plates. These plates were not fixed in place. They moved in different directions because of forces generated inside the Earth. The motion of these plates set the stage for long geological changes that eventually brought continents together and created areas where they collided. The movement of tectonic plates started with energy coming from the interior of the Earth. Heat from radioactive elements and remaining heat from Earth's early formation caused material in the mantle to move in circular patterns. Hot material rose towards the upper mantle, while cooler material sank downward. This continuous movement helped to push and pull the plates resting on top of the mantle. Over millions of years, this motion slowly changed the position of continents and ocean floors. At the beginning of the process that leads to continental collision, there is often the formation of new oceanic crust. This happens at places where plates move apart. Molten material rises from below the crust and cools to form new rock. This new crust spreads outward, pushing older crust away from the center of formation. Over very long time periods, this process creates wide ocean basins between continents. These ocean basins are areas of oceanic crust that continue to grow as long as spreading continues. After a long period of spreading, changes in plate motion can begin. A plate carrying oceanic crust may start to move toward another plate. When two plates move toward each other, a different set of geological processes begins. If one of the plates carries dense oceanic crust, it can move beneath another plate in a process known as subduction. This process takes place at deep ocean trenches. The oceanic crust bends downward and enters the mantle, where it begins to melt due to increasing temperature and pressure. Subduction plays an important role in the eventual collision of continents. When oceanic crust continues to be consumed in the mantle, the distance between continents on either side of the ocean becomes smaller. The ocean basin slowly decreases in size over millions of years. During this time, sediments carried by rivers and ocean currents begin to collect along the edges of continents. These sediments build up in layers and become part of the growing margin of the continental crust. As subduction continues, volcanic activity often develops above the subduction zone. Water and other materials released from the sinking oceanic plate lower the melting point of surrounding mantle rock. This leads to the formation of magma. The magma rises toward the surface and can form volcanic arcs. These volcanic regions add new material to the edge of the continental crust and change its structure over time. The growth of these volcanic arcs contributes to the complexity of the region where eventual collision will occur. In many cases, small pieces of crust, known as terranes, move with oceanic plates. These terranes can include island arcs, fragments of continental crust, and pieces of ocean floor. When subduction continues, these terranes can become attached to the edge of a continent instead of being pulled into the mantle. This process is known as accretion. Accretion increases the size of continents and adds different types of rock to their margins. Over long periods, repeated accretion events build wide and complex continental edges. As oceanic crust continues to be consumed, the space between continents becomes narrower. The remaining ocean basin becomes smaller and shallower in some regions. Sediments continue to fill parts of the ocean floor. Pressure and heat begin to affect these sediments, turning them into hardened rock layers. These rock layers can become folded and faulted due to the movement of tectonic plates. The increasing pressure in the region becomes an important factor in later stages of collision. The movement of plates is not always smooth or constant. Changes in direction and speed can occur due to variations in mantle convection. These changes can affect how quickly an ocean closes. When two continental masses approach each other, the density of continental crust prevents it from easily sinking into the mantle. Continental crust is less dense than oceanic crust, so it resists subduction. This resistance causes strong interactions at the boundary where the plates meet. As the ocean between two continents becomes very narrow, fragments of oceanic crust may remain trapped between the approaching continents. These fragments can be compressed and deformed. The pressure builds in the surrounding rocks, causing folding, faulting, and thickening of the crust. The edges of both continents begin to experience strong deformation. Rocks in these regions are pushed upward and downward due to the force of convergence. Before full collision occurs, there is often a stage where the ocean floor becomes highly fragmented. Sections of oceanic crust may break apart and be forced upward. Some parts may be scraped off and added to the edges of continents. These scraped materials form thick zones of mixed rock types known as accretionary complexes. These complexes contain sediments, volcanic rocks, and pieces of oceanic crust that have been altered by pressure and heat. As convergence continues, the remaining oceanic crust is gradually consumed. The two continental masses move closer together until they reach direct contact. At this stage, subduction of oceanic crust becomes difficult because there is very little oceanic material left. The buoyancy of continental crust prevents it from sinking easily into the mantle. This leads to a strong build-up of pressure at the collision zone. When the continents make contact, the process of continental collision begins. The crust at the boundary is subjected to intense compression. Rocks are folded, fractured, and stacked in layers. Large-scale fault systems develop, allowing sections of crust to move over one another. These faults can extend over long distances and affect deep portions of the crust. The pressure causes the crust to thicken significantly in the collision zone. The thickening of the crust results from horizontal compression and vertical movement of rock layers. As rocks are pushed together, they have no space to move outward freely. This causes them to move upward, forming elevated regions. Deep within the crust, rocks are subjected to high pressure and temperature. These conditions lead to changes in mineral structure and rock type. Metamorphic processes become active in these deep regions. During continental collision, large mountain belts begin to form. These mountain belts develop from the accumulation of folded and faulted rock layers. The crust becomes highly deformed over wide areas. The structure of the crust in these regions becomes very complex, with many overlapping layers of rock. The thickness of the crust increases far beyond its normal state due to continuous compression. The deep parts of the collision zone may experience partial melting. Heat generated from pressure and radioactive decay can cause some rocks to melt and form magma. This magma can rise toward the surface and contribute to volcanic activity in certain regions. However, volcanic activity in continental collision zones is generally less widespread than in subduction zones involving oceanic crust. The process of continental collision also affects the mantle beneath the crust. The downward movement of material during earlier subduction phases changes the flow patterns in the mantle. When oceanic subduction slows or stops, mantle movement adjusts to the new conditions. These changes influence the long-term evolution of the collision zone and surrounding regions. As compression continues over very long time periods, the crust becomes increasingly thick and unstable. Fault systems remain active and continue to move rock layers. Some regions experience uplift, while others experience deep burial of rock layers. These movements create variations in elevation and structure across the collision zone. Sediments continue to accumulate in surrounding basins formed by crustal bending. The edges of the colliding continents may contain ancient rock formations, sedimentary layers, and volcanic materials that have been transported from distant locations. These materials are mixed together during the collision process. The resulting geological structures contain records of earlier stages of ocean formation, subduction, and accretion. These records are preserved in folded and faulted rock sequences. In some areas of continental collision, large-scale thrust faults develop. These faults allow sections of crust to move over other sections for long distances. The movement along these faults contributes to crustal thickening and surface deformation. Rocks along these faults experience high pressure and are often transformed into new mineral forms. These changes occur over long periods of geological time. Deep within the collision zone, the crust may reach conditions where rocks flow slowly under pressure. This flow occurs over very long time scales and contributes to the redistribution of material within the crust. The movement of material at depth affects surface structures and contributes to continued uplift in mountain regions. Sedimentary basins near collision zones can also be affected by the weight of thickened crust. The weight causes the crust to bend downward, creating areas where sediments accumulate. These basins continue to receive material eroded from nearby elevated regions. The interaction between uplift and erosion contributes to continuous changes in the landscape above the collision zone. As continental collision progresses, the original boundary between the continents becomes difficult to identify due to intense deformation. Rock layers become folded, broken, and repositioned over long distances. The structure of the crust in these regions reflects multiple stages of geological activity that occurred over millions of years. The sequence of processes leading to collision remains recorded in the arrangement of rock types and structural features. Heat flow in collision zones is affected by the thickened crust. The movement of heat from the interior of the Earth is altered by changes in crustal thickness. This can influence the formation of minerals and the stability of rock structures. High pressure conditions in deep regions contribute to the formation of new metamorphic rocks with distinct mineral compositions. Fluids released from deep rocks during metamorphism can move through cracks and faults in the crust. These fluids can alter the chemical composition of surrounding rocks. The movement of fluids plays a role in the development of mineral deposits in collision zones. These processes occur gradually over long periods of time and are linked to the evolving structure of the crust. The final stages of continental collision involve continued compression and thickening of the crust. Even after full contact between continents, movement does not stop immediately. The forces generated by mantle convection continue to act on the plates. This leads to ongoing deformation, uplift, and internal changes within the collision zone. The crust remains active and continues to adjust to pressure conditions deep within the Earth. Plate tectonics played a central role in the assembly of the landmass known as Pangea, through a long sequence of movements of the Earth's lithosphere over many hundreds of millions of years. The lithosphere is made up of large rigid sections known as tectonic plates. These plates include continental crust and oceanic crust. The motion of these plates occurs over the asthenosphere, which is a slowly moving, deformable layer beneath the lithosphere. The movement of plates is driven by internal earth heat that creates motion within the mantle. This motion allows plates to shift their positions across the surface of the Earth over very long periods of geological time. The formation of Pangea required the existence of earlier continental fragments that were already present on the Earth's surface. These fragments existed as separate landmasses that had formed and broken apart during earlier stages of Earth history. The movement of tectonic plates caused these fragments to travel across ocean basins. The motion was gradual and continuous over extremely long intervals. As plates moved, ocean basins opened and closed due to the creation and destruction of oceanic crust at plate boundaries. The process of creating new oceanic crust occurred at mid-ocean ridges where magma rose from the mantle and solidified to form new seafloor. The process of destroying oceanic crust occurred at subduction zones where one plate moved beneath another and descended into the mantle. The arrangement of continents on the Earth's surface changed repeatedly due to these processes. Continental fragments that were once separated by wide oceanic spaces were brought closer together, as oceanic crust between them was consumed at subduction zones. The movement of tectonic plates caused the edges of continents to interact with one another along convergent boundaries. These convergent boundaries were locations where crustal shortening occurred. Crustal shortening involved the compression and thickening of the lithosphere. This thickening produced large regions of deformation in the form of folded rock layers, fault zones, and deeply buried crustal materials. As continental fragments moved toward each other, the ocean basins that separated them gradually became narrower. The reduction in ocean basin width occurred because subduction zones continuously consumed oceanic crust. When the supply of oceanic crust between two approaching continental masses became limited, the remaining oceanic space continued to shrink until direct contact between continental margins occurred. This contact marked the beginning of continental collision. Continental collision involved the interaction of thick, buoyant crustal blocks that resisted subduction due to their relatively low density. As a result, deformation was distributed over wide regions of crustal material. During the long sequence of plate movements, several major continental fragments were involved in the assembly process. These fragments included landmasses that had previously been part of older supercontinents that had broken apart during earlier geological intervals. After fragmentation, the pieces of these earlier supercontinents drifted on separate tectonic plates. Over time, plate motion directed these fragments toward new positions on the globe. The motion of these plates was not uniform in direction or rate, and it varied depending on interactions at plate boundaries. The assembly of Pangea involved repeated episodes of ocean closure. Ocean closure occurred when oceanic lithosphere was fully consumed at subduction zones. Once an ocean basin closed, the continental fragments that had been separated by that ocean came into direct contact. This process repeated across multiple regions of the Earth. Each closing ocean contributed to the gradual joining of continental blocks. The final result of these repeated closures was the formation of a continuous or nearly continuous landmass that contained most of the Earth's continental crust. Plate tectonics also influenced the arrangement of mountain belts during the assembly process. Mountain belts formed along zones of crustal deformation at convergent boundaries. When continental fragments moved together, large amounts of crust were compressed. This compression caused folding of rock layers, thrust faulting, and thickening of the crust. As crust thickened, portions of it were uplifted. Uplifted regions formed extensive elevated terrains. These terrains marked the zones where continental fragments had joined. The motion of tectonic plates responsible for assembling Pangea involved several types of plate boundaries. Divergent boundaries created new oceanic crust and allowed plates to move apart. Convergent boundaries caused plates to move toward each other and allowed oceanic crust to be consumed. Transform boundaries allowed plates to move laterally past each other. These boundary interactions controlled the overall pattern of continental movement. The combination of these boundary types produced a dynamic system of plate motion that reorganized the surface of the Earth over long periods. The internal heat of the Earth played a key role in sustaining plate motion. Heat within the mantle produced convectional movement of solid but slowly flowing rock. This movement caused stresses at the base of tectonic plates. These stresses contributed to the motion of plates across the surface. The transfer of heat from the deep Earth to the surface also contributed to volcanic activity at certain boundaries. Volcanic activity added new material to the crust at divergent boundaries, while subduction zones recycled crustal material back into the mantle. As plate motion continued, continental fragments experienced repeated cycles of separation and convergence. During separation phases, continental blocks moved apart due to the formation of new oceanic crust at spreading centers. During convergence phases, oceanic crust was consumed and continents moved closer together. These cycles of movement played a direct role in shaping the arrangement of continents that eventually became part of Pangea. The process of continental assembly also involved the accretion of smaller landmasses onto larger continental margins. These smaller landmasses included island arcs and microcontinents that were carried by moving oceanic plates. When these smaller fragments reached subduction zones, they were added to the edges of larger continents instead of being fully subducted. This process contributed additional crustal material to growing continental regions. Over time, multiple accretion events increased the size of continental blocks. As ocean basins narrowed, sediment accumulated along continental margins. These sediments were transported by erosion from land areas and deposited in marine environments. When continental collision occurred, these sedimentary deposits were compressed and incorporated into mountain belts. The deformation of sediments added to the structural complexity of the zones where continents joined. Layers of sediment were folded, faulted, and transformed under conditions of increased pressure and temperature within the crust. The formation of Pangea required the closure of several large ocean systems. These ocean systems separated major continental fragments for long geological intervals. Subduction zones around the margins of these oceans continuously consumed oceanic crust. As the process continued, the oceanic basins became progressively smaller. The reduction in oceanic area brought continental margins closer together until direct contact occurred. Once contact was established, further convergence resulted in extensive crustal deformation. Plate tectonics also controlled the timing of continental assembly events. The rate of plate motion influenced how quickly ocean basins closed. Changes in mantle convection patterns affected the direction of plate movement. These changes occurred over long periods and influenced the pathways followed by continental fragments. The arrangement of subduction zones around ocean basins also affected how efficiently oceanic crust was consumed. The assembly of Pangea involved interactions between multiple plates operating simultaneously. Each plate moved according to forces acting along its boundaries. These forces included slab pull at subduction zones, ridge push at mid-ocean ridges, and basal drag from mantle flow. Slab pull occurred when dense oceanic lithosphere descended into the mantle, pulling the rest of the plate along. Ridge push occurred when newly formed crust at mid-ocean ridges moved away from elevated ridge regions due to gravitational forces. Basal drag occurred when mantle flow exerted frictional forces on the base of plates. As these forces acted over long periods, continental fragments gradually migrated across the surface of the Earth. Their movement led to repeated interactions between landmasses. Each interaction modified the structure of the crust at plate boundaries. These modifications included the formation of fault systems, the development of fold belts, and the thickening of continental lithosphere. Over time, these processes contributed to the construction of a continuous continental mass. The assembly process also involved the progressive reorganization of ocean basins. As continents moved, ocean basins were reshaped by the creation and destruction of seafloor. Mid-ocean ridges produced new crust that expanded ocean floors. Subduction zones removed crust from the edges of ocean basins. The balance between these processes determined the size and shape of oceans surrounding continental fragments. As continental fragments approached each other, stress within the lithosphere increased. This stress led to deformation of rocks over wide regions. Deformation included folding of layered rocks, fault displacement, and metamorphism of existing rock materials. Metamorphism involved changes in mineral structure due to increased pressure and temperature. These changes altered the physical and chemical properties of crustal rocks within collision zones. The progressive joining of continental fragments created large-scale zones of crustal thickening. These zones formed where multiple tectonic events accumulated over time. Each event added additional layers of deformation. The accumulated deformation recorded the history of plate movement, leading to continental assembly. The structural patterns preserved in these zones reflect the sequence of tectonic interactions that occurred during the formation of Pangea. Plate tectonics also influenced the distribution of volcanic activity during the assembly process. Volcanic activity occurred mainly along subduction zones and rift zones. At subduction zones, melting of descending oceanic lithosphere produced magma that rose toward the surface. At rift zones, decompression, melting of mantle material produced magma that formed new crust. These volcanic processes contributed to the recycling and creation of crustal material during the assembly process. The interaction of tectonic plates over long periods led to repeated cycles of ocean opening and closing. These cycles influenced the positions of continents on the Earth's surface. Each cycle involved the breakup of earlier continental arrangements, followed by the movement of fragments across newly formed ocean basins. The eventual convergence of these fragments resulted in the assembly of large continental masses. The final assembly of Pangea occurred when multiple continental fragments that had previously been separated by different ocean basins came into direct contact through sustained plate motion. The closure of these ocean basins occurred at different times and locations. Each closure contributed to the enlargement of the continuous continental area. The combined effect of these closures produced a single large landmass containing most of the Earth's continental crust. The time period when Pangea fully existed refers to a long span of geological time, during which most of Earth's continental land was joined into a single large landmass. This time did not begin suddenly, and it did not end abruptly. It developed through gradual geological changes and remained in a stable joined condition for a limited interval in Earth history. This interval is placed within the late part of the Paleozoic era and extended into the early part of the Mesozoic era. The full existence of this supercontinent is most closely associated with the late Carboniferous period, the Permian period, and the earliest part of the Triassic period. These periods form a continuous sequence of Earth history during which continental landmasses were assembled, remained joined, and then began to separate. The late Carboniferous period marks an important stage in the development of this global land arrangement. During this time, major continental blocks that had been separate for long intervals of Earth history began to move toward each other through slow motion of Earth's lithospheric plates. These movements were not sudden events, but involved steady motion across very long spans of time. By the later part of the Carboniferous period, many continental fragments had already made contact along broad collision zones. These collisions created large mountain systems and extended zones of crustal deformation. The joining of continental regions during this time formed the foundation of a nearly complete supercontinent structure. As the Carboniferous period continued into its later stages, the arrangement of land became increasingly unified. Large sections of what would become the supercontinent were already connected. Shallow inland seas that had previously separated land areas became reduced in extent as landmasses moved closer and collided. Sediments accumulated in these shrinking marine regions, recording changes in sea level and crustal movement. The joining of continental blocks during this time contributed to a continuous land surface that extended across vast regions of the planet. This stage represents the beginning of the full assembly phase that led into the period of complete existence. The transition from the late Carboniferous period into the Permian period marks the interval in which the supercontinent reached its most complete and continuous form. During the early Permian period, most major continental blocks were already connected in a single arrangement. This included large land areas that had previously been distributed across different hemispheres of Earth. The crustal plates carrying these landmasses had completed most of their convergence. The boundaries between them were marked by extensive mountain belts, formed through long-lasting compression of Earth's crust. During the Permian period, the supercontinent maintained a broad and continuous land surface. Geological processes during this time were strongly influenced by the presence of a single dominant landmass. The interior regions of the supercontinent experienced widespread deposition of sediments carried by river systems. These river systems developed across long distances, transporting materials from elevated regions formed by earlier collisions. The arrangement of drainage systems was directly connected to the structure of the landmass and its elevation differences created by tectonic activity. The climate patterns during this period were shaped by the configuration of the supercontinent. Large interior regions were distant from oceanic moisture sources, and this influenced patterns of dryness in many areas. Coastal regions experienced different conditions influenced by nearby ocean basins surrounding the supercontinent. These ocean basins surrounded the landmass on almost all sides, forming a continuous global ocean system. The interaction between land and ocean during this time contributed to sediment formation along continental margins and within shallow marine environments. The Middle Permian period represents a phase in which the supercontinent remained fully assembled and structurally stable in its overall configuration. The movement of tectonic plates continued, but these movements involved smaller adjustments within the larger joined landmass. Mountain belts that had formed during earlier collisions remained active in some regions due to ongoing crustal compression and uplift. Other regions experienced gradual stabilization, where erosion became a dominant process, shaping the landscape over long intervals. Throughout the Permian period, volcanic activity occurred in various regions associated with plate boundaries and internal crustal structures. These volcanic processes contributed to the release of materials from Earth's interior to the surface. Basaltic and other volcanic deposits accumulated in certain areas, adding to the geological record of this time. Magmatic activity was closely related to the dynamics of crustal stress and mantle processes beneath the supercontinent. Sedimentary basins developed in many parts of the supercontinent during the Permian period. These basins collected large volumes of sediments from surrounding highlands. Rivers carried sand, silt and clay into these low-lying areas, where they accumulated in thick layers over long periods. Some basins contained alternating layers of sediment that recorded repeated changes in environmental conditions. The formation of these basins was directly linked to crustal bending, stretching and sinking caused by tectonic forces. The fossil record preserved within Permian-aged rocks provides evidence of ecosystems that existed across the supercontinent during its full existence phase. These ecosystems were distributed across vast continuous land areas. Plant life included various types of vegetation adapted to different moisture conditions. Animal life included diverse groups that inhabited terrestrial environments, freshwater systems, and coastal regions. The distribution of life forms was influenced by the continuous nature of the landmass, which allowed movement across large distances without major oceanic barriers. The late Permian period marks a continuation of the fully assembled condition of the supercontinent. During this time, the landmass remained intact, with no major fragmentation into separate continents. Geological activity continued along internal and external boundaries of the crust. Subduction zones along the edges of the surrounding oceanic basins remained active, leading to recycling of oceanic crust into the mantle. These processes maintained the long-term dynamics of Earth's surface even while the supercontinent remained assembled. As the Permian period progressed toward its later stages, subtle changes in plate motion began to influence the internal structure of the supercontinent. These changes did not immediately lead to separation, but involved gradual reorganization of stress within the crust. Fault systems developed in some regions as a response to these internal forces. These faults allowed limited movement within the continental interior, while the larger landmass remained connected. The transition from the Permian period into the Triassic period marks the beginning of the interval in which the fully assembled condition of the supercontinent started to change. At the beginning of the Triassic period, the landmass still existed as a continuous structure, although internal tectonic adjustments became more pronounced. Early Triassic time continued to reflect conditions associated with a joined continental arrangement. Large regions of land remained connected, and ocean basins still surrounded the supercontinent. During the earliest part of the Triassic period, sedimentation continued across continental interiors and margins. River systems maintained their long pathways across the landmass, transporting materials across wide areas. Basins continued to receive sediment deposits, and volcanic activity persisted in regions influenced by tectonic stress. The structural continuity of the supercontinent remained present during this interval, even as internal changes increased in complexity. The early Triassic period also records changes in environmental conditions across the supercontinent. Geological records indicate shifts in sediment types and distribution patterns within basins. These changes reflect ongoing adjustments in Earth's surface systems. The presence of a continuous landmass still influenced large-scale circulation of atmospheric and oceanic systems around its margins. Ocean basins surrounding the landmass remained extensive and connected, forming a global marine system that interacted with the edges of the supercontinent. The fully existing phase of Pangea is therefore associated with a continuous interval extending from the late Carboniferous period through the entire Permian period and into the early part of the Triassic period. Within this interval, the most complete stage of assembly is placed in the Permian period, when nearly all continental fragments were joined into one landmass. The late Carboniferous period represents the stage of final assembly, and the early Triassic period represents the stage during which continuity still existed before significant separation processes became established. The geological structure of the supercontinent during its full existence phase involved a complex arrangement of crustal blocks joined along long collision zones. These zones were regions where Earth's lithospheric plates had converged over extended time. The convergence produced thickened crust in many regions, which contributed to elevated landforms. These elevated regions were subject to erosion, which redistributed material across lower areas of the land mass. The erosion process operated continuously across the full duration of the supercontinent's existence. Deep within the crust, heat and pressure conditions influenced rock transformation. Metamorphic processes occurred in regions affected by earlier collisions. Rocks that had originally formed in different conditions were altered into new forms due to burial and deformation. These processes occurred over long geological timescales and contributed to the complexity of the crust beneath the supercontinent. Mantle dynamics beneath the supercontinent also played a role in its maintenance during its full existence. Heat from Earth's interior influenced convection patterns in the mantle, which in turn affected the movement of tectonic plates. Although the supercontinent remained joined, internal motion continued within Earth's deeper layers. These processes maintained the long-term evolution of the planet's surface structure. The surrounding ocean system during this time formed a continuous global body of water that surrounded the supercontinent. Oceanic crust was created at mid-ocean ridges and destroyed at subduction zones along continental margins. This recycling of oceanic crust occurred continuously throughout the existence of the supercontinent. Sediments derived from continental erosion were transported into ocean basins, where they accumulated along continental margins and deep-sea environments. The interaction between land and ocean during the full existence phase influenced the distribution of sediments, the formation of marine basins, and the development of coastal environments. These processes operated continuously throughout the late Paleozoic and early Mesozoic intervals associated with the supercontinent. The configuration of Earth's surface during this time allowed large-scale geological systems to function across connected land and ocean regions. The stability of the supercontinent during its full existence phase was not absolute in terms of internal geological activity. Instead, it involved a balance between ongoing tectonic movement and overall structural continuity. While the landmass remained joined, internal deformation continued in various regions. This included folding of rock layers, faulting, volcanic intrusion, and gradual uplift and subsidence of crustal blocks. The end of the early Triassic period marks the interval after which significant fragmentation processes began to affect the structure of the supercontinent. Before this transition, the landmass had maintained its continuous configuration over a long span of geological time that included the late Carboniferous period, the Permian period, and the early Triassic period. This interval represents the complete phase of existence in which the supercontinent remained assembled as a single dominant landmass on Earth. long before the landmasses of Earth came together into the arrangement known as Pangea, the surface of the planet went through repeated stages of gathering and separating large blocks of continental crust. These earlier arrangements of continents formed over vast spans of time stretching back to nearly 4 billion years ago. At those early times, the Earth was still developing a stable outer layer. The crust was forming, breaking and reforming as heat from inside the planet moved upward through volcanic activity and mantle movement. Small pieces of continental material slowly appeared, joined, and then shifted apart again as internal forces continued to reshape the surface. Over time, these small pieces began to gather into larger units of land, and these larger units are described as early supercontinents. One of the earliest proposed large continental assemblies is known as Valbara. It is thought to have existed around 3 billion years ago. At that time, the Earth's crust was still very active and unstable in many regions. The land that formed Valbara came from very old pieces of continental crust located in regions that are now part of southern Africa and Western Australia. These crustal blocks contain ancient rocks that show similar ages and similar geological features. These similarities suggest that they were once connected as part of a single large landmass. The formation of Valbara involved gradual movement of crustal sections as heat from the Earth's interior caused slow motion in the rocky outer shell. Over long periods, volcanic material added new crust, and older crust was reshaped and pushed together into larger formations. After the time associated with Valbara, other large continental assemblies developed. One of these was called Ur. It is believed to have formed around 3 billion years ago as well, possibly existing alongside Valbara in some form or replacing parts of it as crustal movements continued. Ur included regions that are now found in parts of India, Australia, and Africa. The crustal sections that formed Ur show signs of deep geological stability in certain areas, meaning that they remained intact for long periods while surrounding regions changed. The rocks from these regions show evidence of high temperature and pressure conditions, which indicate that deep crustal processes were active during the formation of this early continental assembly. The formation of Ur involved repeated cycles of crust creation and crust thickening, which gradually increased the size of stable continental regions. As time continued, another major continental assembly began to form known as Kenorland. This structure is thought to have existed around 2,500 million years ago. Kenorland included large parts of what are now North America, Greenland, Scandinavia, and other regions. The formation of Kenorland involved the merging of several older continental fragments. These fragments moved across the surface of the Earth as heat-driven motion within the mantle caused slow shifting of the crust. When these fragments came together, they formed a larger and more continuous landmass. Geological evidence for Kenorland includes matching rock types and similar ages of mineral formations found in distant continents today. These similarities suggest that these regions were once joined in a single large continental structure. During the time of Kenorland, the Earth was also experiencing major changes in its atmosphere and oceans. The interaction between land and water contributed to chemical changes in surface environments. Volcanic activity released gases that interacted with ocean water, and these processes affected the composition of the early atmosphere. The presence of large continental areas influenced how heat was distributed across the planet's surface, and this affected the movement of ocean currents and the formation of sediment layers. As Kenorland existed, it eventually began to break apart due to continued internal motion within the Earth. This breaking apart created smaller continental blocks that later became part of new assemblies. After the fragmentation of Keenorland, another large continental structure known as Columbia, also referred to as Nuna in some scientific interpretations, began to form around 1,800,000,000 years ago. Columbia was one of the most extensive early supercontinental arrangements known from geological evidence. It brought together many continental blocks that had previously been separated. These blocks included regions that are now part of North America, South America, Antarctica, Australia, Africa, and parts of Eurasia. The formation of Columbia involved long periods of crustal collision, where moving sections of the Earth's surface slowly came together, as internal heat-driven processes continued beneath them. The rocks associated with Columbia show evidence of high-grade metamorphism in several regions, indicating that they were subjected to strong pressure and heat during the assembly of this large landmass. The continental crust thickened in many areas as fragments joined together. Over time, stable interior regions developed where the crust remained relatively unchanged for long periods. These stable regions are important in understanding how early continents remained intact for hundreds of millions of years. Columbia existed for a very long span of time before it began to break apart around 1,300,000,000 years ago. The breaking of Columbia involved the development of rifts within the continental mass. These rifts gradually widened as internal forces within the Earth caused the crust to stretch and weaken in certain areas. As the landmass broke apart, new ocean basins began to form between the separating continental blocks. The separation of Columbia created new pathways for ocean circulation and changed the distribution of land and sea on the planet. After the breakup of Columbia, the continental fragments continued to move and eventually came together again in a new arrangement known as Rodinia. Rodinia began forming around 1,100,000,000 years ago and reached a more complete structure around 900,000,000 years ago. The formation of Rodinia involved the collision of many continental pieces that had previously been separated after the breakup of Columbia. These collisions caused thickening of the crust and the formation of large mountain-building zones in several regions. The crustal movement during this time was driven by heat flow within the Earth, which caused slow but continuous motion of the surface plates. Rodinia included landmasses that are now part of North America, South America, Africa, Antarctica, Australia, and parts of Asia. These regions were positioned differently than they are today, and their arrangement formed a large connected land surface. The interior of Rodinia contained stable continental areas, while the edges experienced more active geological processes. These edge regions were sites where new crust was formed, and where older crust was recycled into the Earth's interior through subduction processes. During the existence of Rodinia, environmental conditions on Earth also changed significantly. The arrangement of continents influenced ocean circulation patterns and the distribution of heat across the planet's surface. The presence of a large continuous landmass affected how sediments were deposited and how erosion occurred in different regions. Over time, Rodinia began to break apart around 750,000,000 years ago. This breakup involved the development of rift zones that separated the continental blocks. These rift zones expanded as internal forces continued to act on the crust, leading to the formation of new ocean basins between the separating landmasses. The breakup of Rodinia produced several smaller continental units that drifted across the Earth's surface. These units later became part of other continental assemblies. The movement of these landmasses continued over long periods, and the Earth's surface remained in a state of ongoing reorganization. The fragments of Rodinia did not remain isolated for long geological periods, as internal forces within the Earth continued to move them toward new configurations. After Rodinia, another large continental arrangement, known as Pangea, formed around 600 million years ago. Pangea was a relatively short-lived supercontinental structure compared to earlier ones. It formed through the convergence of several continental blocks that had separated from Rodinia. The assembly of Pangea involved the joining of landmasses that surrounded an oceanic region, and this led to the creation of a large but temporary continental configuration. The existence of Pangea was followed by another phase of breakup around 540 million years ago. During this time, the continental blocks that formed Pangea began to separate again, creating new ocean basins and dispersing landmasses across the planet's surface. These changes set the stage for later continental movements that eventually led to the formation of Pangea much later in Earth's history. Throughout the time of these early supercontinents, the Earth's crust was constantly reshaped by internal processes. Heat from the interior of the planet caused continuous motion in the rocky outer layer. This motion led to the repeated assembly and breakup of large continental structures. Each supercontinent formed through the slow joining of smaller continental fragments, and each breakup resulted in the redistribution of those fragments into new positions. The cycle of assembly and separation continued over hundreds of millions and billions of years. The rocks that remain today from these early supercontinents provide important records of Earth's geological history. These rocks include mineral structures that formed under high pressure and temperature conditions. They also include sedimentary layers that show how ancient environments changed over time. The distribution of these rocks across different continents today allows scientists to identify past connections between landmasses that are now widely separated. The movement of continental fragments during these early times was influenced by processes within the Earth's mantle. The mantle is a deep layer beneath the crust where solid rock moves slowly over long periods. This movement creates forces that push and pull the crust, causing it to break, drift, and merge. These processes operate continuously, and they played a central role in the formation of each early supercontinent. As continental blocks moved across the surface of the Earth, they interacted with ocean basins that formed between them. These interactions affected the shape and size of oceans over time. When continents came together, ocean basins became smaller or disappeared entirely in some regions. When continents separated, new ocean basins formed as magma rose from beneath the crust and created new seafloor. The early supercontinents also influenced the distribution of minerals and natural resources within the Earth's crust. As continents collided, rocks were compressed and transformed, creating new mineral structures. As continents separated, volcanic activity brought new material to the surface, adding layers of rock and reshaping the crust. These processes occurred repeatedly during each cycle of supercontinent formation and breakup. The time periods associated with these early supercontinents span from nearly 4 billion years ago to several hundred million years ago. Each stage represents a different arrangement of Earth's landmasses, shaped by continuous internal motion. The gradual transformation of the planet's surface during these times reflects the long-term nature of geological processes that operate beneath the crust. The transitions between Valbara, Kenorland, Columbia, Rodinia, and Pangea show a sequence of large-scale changes in the arrangement of continental crust. Each of these structures formed from the merging of smaller fragments and later broke apart into new configurations. The movement of these fragments continued across all time periods involved, with no long-term fixed positions for the continents. The distribution of ancient rock formations across present-day continents provides evidence for these early supercontinents. Similar rock ages, mineral compositions and structural patterns appear in regions that are now far apart. These similarities indicate that those regions were once connected within larger continental structures. The study of these rock formations helps reconstruct the history of continental movement over vast spans of time. The early supercontinents existed during a time when Earth's internal heat was higher than it is in later periods. This higher internal heat contributed to more active crustal motion and more frequent changes in continental arrangements. The repeated cycles of assembly and breakup reflect the ongoing transfer of heat from the Earth's interior to its surface through geological processes that shaped the entire structure of the planet over long durations that continue into later eras, leading toward the time when Pangea begins to form from later continental fragments that trace their origins back through these earlier stages of continental organization. Global climate conditions during the period when the supercontinent Pangea existed were shaped by the arrangement of all major land areas into a single connected mass surrounded by a vast global ocean. This arrangement influenced the movement of air, the flow of moisture, the distribution of heat from the sun, and the behavior of seasonal weather patterns across the entire planet. The landmass stretched across a wide range of latitudes, from regions close to the equator to areas reaching far into polar zones. Because of this wide spread, different parts of the planet experienced very different climate conditions at the same time, yet all were influenced by the same global structure of land and ocean. The atmosphere during this time contained a different balance of gases from what is present in later geological periods. Carbon dioxide levels remained higher than modern values for long intervals. This supported stronger warming effects in the lower atmosphere. Oxygen levels were present in amounts sufficient to support complex life forms, but their distribution and stability varied through long periods due to biological activity and volcanic emissions. Large volcanic regions released gases into the atmosphere, including carbon dioxide, sulfur compounds, and water vapor. These emissions influenced cloud formation, rainfall patterns, and long-term atmospheric stability. The global circulation of air moved in large patterns that were strongly shaped by the continuous land surface. Warm air rose near equatorial regions where solar heating was strongest. This air moved toward higher latitudes at upper atmospheric levels before descending in other regions. This movement created zones of rising and sinking air that influenced rainfall distribution. Large interior regions of the supercontinent received limited moisture because air masses lost much of their water content before reaching deep inland areas. This produced widespread dry conditions in central land regions. Coastal regions received more moisture because of their direct connection to ocean evaporation sources. Seasonal changes affected different parts of the supercontinent in strong ways. Areas near the equator experienced repeated cycles of wet and dry conditions driven by shifting wind belts. These shifts moved rain-bearing air masses across certain regions at different times of the year. During wet phases, intense rainfall supported river systems and temporary lakes. During dry phases, evaporation increased and water bodies shrank, leaving exposed dry land surfaces. These cycles continued over long periods and influenced soil formation and surface conditions. In higher latitude regions, seasonal variations included extended periods of reduced sunlight during parts of the year and extended periods of continuous daylight during other parts. These conditions influenced temperature patterns and the timing of biological activity. Snow and ice formed in colder intervals, especially in regions closer to the poles. Ice accumulation occurred on land surfaces during colder phases, and melting occurred during warmer phases, producing meltwater flows that shaped valleys and sediment deposits. The interior regions of the supercontinent remain dry for long intervals due to limited access to ocean moisture. Air moving inland lost moisture during travel, leaving very little precipitation for central areas. These regions developed extensive dry land environments with sparse water availability. Wind activity shaped loose surface materials, moving fine particles across wide distances. Dust transport influenced soil composition in other parts of the landmass when winds carried particles outward toward coastal zones. Coastal regions experienced higher humidity levels because of continuous evaporation from the surrounding ocean. Warm ocean surfaces released water vapor into the air, which then moved on to nearby land areas. This moisture supported rainfall events, river formation, and dense vegetation growth in suitable regions. River systems carried water from elevated areas toward coastal basins, creating large drainage networks that transported sediments and dissolved materials. Ocean conditions surrounding the supercontinent played an important role in regulating climate. Ocean currents moved heat from equatorial waters toward higher latitudes. These currents also returned cooler water toward tropical regions. The arrangement of the supercontinent influenced the direction and strength of these flows. Large coastal boundaries affected how water circulated around the planet, shaping temperature distribution in marine environments. Evaporation from ocean surfaces contributed to atmospheric moisture, which later returned as rainfall over land and sea. Monsoon systems developed in several regions due to seasonal shifts in heating between land and ocean surfaces. During periods when land surfaces heated strongly under sunlight, air rose above continental interiors and drew moist air inward from surrounding ocean areas. This process brought heavy rainfall to certain coastal and nearby inland regions. During cooler phases, wind patterns shifted direction, reducing moisture inflow and leading to drier surface conditions. These repeated cycles shaped long-term sediment patterns and soil layering. Large desert regions formed in central parts of the supercontinent. These desert zones developed due to persistent dryness, limited cloud formation, and strong surface heating during daylight periods. Temperature changes between day and night were significant in these regions. Heat accumulated quickly on exposed surfaces during sunlight exposure, while rapid cooling occurred after sunset. These cycles influenced rock breakdown and sediment production. Volcanic activity during this period released large amounts of gases and ash into the atmosphere. These emissions influenced climate conditions on both short and long-time scales. Ash particles in the atmosphere reduced sunlight reaching the surface for limited periods, affecting temperature and weather patterns. Over longer intervals, volcanic gases contributed to atmospheric composition changes that influenced heat retention and precipitation behavior. Volcanic regions also created localized heating effects in surrounding environments. Rainfall distribution across the supercontinent was uneven. Regions closer to moisture sources received regular precipitation, while interior regions received limited rainfall. Some areas experienced seasonal rainfall that arrived in concentrated periods, followed by long, dry intervals. This pattern influenced river behavior, with some rivers flowing continuously, while others flowed only during wet phases. Lakes in certain regions expanded and contracted, based on rainfall variability and evaporation rates. Vegetation during this time adapted to the wide range of climate conditions. In wetter regions, dense plant growth developed along river systems and coastal zones. In drier regions, plant life existed in scattered forms, surviving in locations where water was available for longer periods. Plant distribution influenced soil stability, as root systems held surface materials in place during rainfall and wind events. Atmospheric circulation patterns also influenced storm development. Storm systems formed when warm, moist air rose rapidly and cooled at higher altitudes. These storms produced heavy rainfall events in certain regions. Storm frequency and intensity varied based on seasonal shifts and regional temperature differences. Some storms extended across large areas, affecting both coastal and inland environments. Dust and aerosol particles in the atmosphere played a role in climate regulation. Fine particles lifted from dry land surfaces entered the air and travelled long distances. These particles influenced cloud formation by providing surfaces for water vapour to condense. In some cases, dust reduced sunlight reaching the surface, leading to temporary cooling effects in affected regions. The movement of these particles connected distant parts of the supercontinent through atmospheric transport. Temperature distribution across the planet followed patterns influenced by latitude, elevation, and proximity to ocean water. Equatorial regions maintained higher average temperatures due to consistent solar energy input. Higher latitude regions experienced lower temperatures during parts of the year when sunlight exposure decreased. Elevated land areas had cooler conditions due to thinner atmosphere and reduced heat retention at higher altitudes. Water availability played a central role in shaping climate conditions. Areas with continuous water sources supported higher humidity and more stable local climates. Regions without steady water input experienced stronger dryness and more variable surface conditions. Rivers, lakes, and groundwater systems influenced local atmospheric moisture levels through evaporation and surface exchange. Long-term carbon cycling influenced atmospheric composition. Carbon dioxide entered the atmosphere through volcanic emissions and organic decay processes. It was removed through processes such as rock weathering and biological activity. These processes operated over extended time periods and influenced global temperature conditions by affecting atmospheric heat retention. The arrangement of land and ocean also influenced wind strength and direction. Large continuous land areas allowed winds to travel long distances without interruption. This affected the transport of heat, moisture, and airborne particles. Wind patterns contributed to the formation of dune fields in dry regions and supported moisture transport toward wetter regions. Ice formation occurred in polar regions during colder intervals. Snow accumulated over long periods and compacted into ice layers. These ice-covered regions influenced atmospheric circulation by reflecting sunlight and maintaining cooler surface conditions. Seasonal melting introduced fresh water into nearby ocean areas, affecting local water properties and circulation patterns. Chemical processes in the atmosphere also influenced climate behavior. Reactions involving water vapor, carbon dioxide, and other gases contributed to cloud formation and precipitation events. Sulfur compounds from volcanic emissions reacted in the atmosphere to form particles that influenced sunlight penetration and cloud properties. These processes operated continuously and affected both short-term weather and long-term climate conditions. Soil development across the supercontinent was strongly linked to climate conditions. In wetter regions, soils formed through the accumulation of organic material and mineral breakdown. In dry regions, soil formation occurred more slowly, with limited organic input and strong influence from wind transport. Soil properties influenced water retention and plant distribution, which in turn affected local climate conditions through surface moisture exchange. River systems played a major role in redistributing water across land areas. Water from rainfall and mountain regions flowed through channels toward lower elevation basins. These rivers transported sediments that reshaped landscapes over time. Flooding events occurred during periods of heavy rainfall, spreading water and sediments across surrounding land surfaces and influencing soil formation. Long-term stability of climate conditions was influenced by interactions between land, ocean, atmosphere, and geological activity. Each of these components contributed energy, moisture, and material exchanges that shaped weather patterns across the planet. Variations in any one component influenced the behavior of others through continuous physical and chemical processes, operating over long durations. Surface heating from solar energy remained a constant driver of atmospheric motion. Regions receiving higher sunlight exposure experienced stronger air movement due to rising warm air. This movement created pressure differences that guided wind flow across the supercontinent. These patterns influenced rainfall distribution and temperature variation across different regions. Atmospheric moisture content determined cloud formation and precipitation frequency. Water vapor accumulated in the atmosphere through evaporation from oceans, lakes, and moist land surfaces. When air cooled, this vapor condensed into clouds, eventually producing rainfall. Cloud cover also influenced surface temperatures by regulating sunlight reaching the ground. Long-distance transport of moisture allowed some rainfall to occur far from ocean sources. Air masses carrying water vapor moved across the supercontinent and released moisture when conditions allowed condensation. This process supported rainfall in regions that would otherwise remain dry under local evaporation alone. Surface erosion processes were influenced by rainfall, wind, and temperature changes. Rainfall contributed to mechanical breakdown of rock surfaces, while wind transported loose materials across dry regions. Temperature changes caused expansion and contraction of surface materials, contributing to gradual fragmentation. These processes shaped land surfaces over extended time periods. Panthalassa was the vast global ocean that surrounded the large landmass known as Pangea during a long stage of Earth's geological history. It covered most of the planet's surface and formed a continuous body of seawater, without interruption by large continental divisions. This ocean existed during a time when Earth's land was arranged in a different configuration from today, and its waters spread across the entire outer region of the planet, wrapping around the supercontinent and filling almost all available marine space. The structure of Panthalassa was shaped by long geological processes that involved the movement of Earth's outer rocky shell. This shell is divided into large sections that slowly shift position over very long periods. These sections interacted in ways that created deep ocean areas, raised underwater ridges, and zones where one section of the ocean floor moved beneath another. Over time, these processes formed a complex ocean basin system that defined the physical nature of Panthalassa. The ocean floor of Panthalassa was not uniform. It included regions of deep sea floor, areas of elevated underwater ridges, and broad expanses of basaltic crust formed by volcanic activity. New ocean crust was continuously created at spreading zones where molten material rose from inside Earth and cooled to form solid rock. This process contributed to the renewal of the ocean floor and maintained active geological change across the ocean basin. In many parts of Panthalassa, oceanic crust moved towards zones where it descended back into Earth's interior. These zones were associated with deep trenches that marked areas of intense geological activity. The recycling of oceanic crust played a major role in shaping the structure of the ocean basin. The movement of this crust also influenced volcanic activity across the edges of the ocean and in island regions that formed above these active zones. The waters of Panthalassa covered a wide range of depths. Near the central parts of the ocean, the seafloor reached extreme depths, formed by long geological processes of crustal movement and cooling. Near the margins of the ocean, closer to the edges of Pangea, the seafloor often rose in elevation, forming underwater slopes and continental shelves. These shelves provided areas where shallow marine environments developed along the edges of the supercontinent. The circulation of water within Panthalassa involved movement driven by differences in temperature, salinity, and wind patterns across the ocean surface. These movements formed large-scale flow systems that distributed heat and nutrients throughout the ocean. Surface waters moved across vast distances, while deeper waters circulated through slower movements that connected different layers of the ocean. The atmosphere above Panthalassa interacted directly with the ocean surface. Wind patterns influenced the movement of surface waters, and evaporation processes affected the distribution of moisture in the air. These interactions contributed to patterns of rainfall and dryness across different regions of Pangea, since the ocean played a central role in transferring water vapor into the atmosphere. The ocean floor of Panthalassa contained volcanic structures that formed through continuous geological activity. These structures included underwater mountains created by rising magma. Some of these volcanic features grew large enough to reach the ocean surface, forming islands scattered across the ocean. These islands were often located near zones of tectonic activity, where the ocean floor was especially dynamic. Hydrothermal systems were present in many parts of Panthalassa. These systems formed when seawater moved through cracks in the ocean crust and came into contact with heated rock below the surface. The water became heated and enriched with dissolved minerals before returning to the ocean. These environments supported chemical processes that influenced the composition of seawater and contributed to energy sources within the deep ocean environment. Sediments accumulated across the floor of Panthalassa through the gradual settling of particles from the water column. These particles included remains of marine organisms, volcanic dust, and fine mineral material transported by ocean currents. Over time, sediment layers built up across large areas of the ocean floor, forming thick deposits that recorded long periods of environmental conditions. The biological activity within Panthalassa included a wide range of marine organisms. Microscopic life forms were present throughout the water column and formed the foundation of marine ecosystems. These organisms participated in nutrient cycles and contributed to the movement of energy through the ocean environment. Larger marine organisms inhabited different levels of the ocean, adapting to conditions of depth, temperature, and pressure. Marine ecosystems in Panthalassa were influenced by the availability of nutrients carried by ocean currents. Areas where nutrients were brought upward from deeper waters supported higher concentrations of biological activity. These regions became zones of increased biological productivity, where food chains developed based on the presence of microscopic organisms and small marine animals. The chemical composition of Panthalassa's waters was influenced by interactions between the ocean floor, volcanic activity, and biological processes. Dissolved gases and minerals circulated through the ocean system, and these elements participated in reactions that affected water chemistry. The balance of oxygen and carbon compounds and other dissolved substances played a role in shaping marine environments at different depths. The edges of Panthalassa, where the ocean met the landmass of Pangea, contained coastal marine environments. These environments included shallow waters where sediments accumulated more rapidly due to erosion from the land. Rivers carried large amounts of material from the interior of Pangea into the ocean, contributing to the formation of delta systems and coastal sediment zones. The interaction between land and ocean influenced weather patterns across Pangea. The large ocean surface affected atmospheric circulation, which in turn shaped temperature distribution across different regions of the supercontinent. Moisture from Panthalassa contributed to precipitation in some areas, while other regions experienced limited rainfall, depending on atmospheric movement. Panthalassa contained zones of intense tectonic activity where oceanic plates interacted. These zones were characterized by the movement of the seafloor and the formation of deep fractures in the crust. Volcanic activity was common in these areas, and new material from Earth's interior was continuously introduced into the ocean system. The deep regions of Panthalassa were influenced by high pressure and low temperature conditions. These environments supported specialized forms of life adapted to limited light availability. Biological activity in deep regions relied on chemical energy sources rather than sunlight, especially near hydrothermal vents where mineral-rich fluids supported microbial communities. The surface of Panthalassa was exposed to sunlight, which influenced temperature distribution and biological productivity. Sunlight penetration supported photosynthetic organisms in the upper layers of the ocean. These organisms formed the base of marine food systems and played a role in regulating oxygen levels in the ocean and atmosphere. Ocean currents within Panthalassa were shaped by the rotation of Earth. This rotation influenced the direction of large-scale water movement and contributed to the formation of circulating systems across the ocean basin. These systems transported heat from equatorial regions toward higher latitudes and influenced environmental conditions across vast areas of the ocean. The physical size of Panthalassa created conditions where water movement occurred over extremely long distances. Energy transfer within the ocean involved interactions between wind, surface water, and deeper circulation layers. These processes contributed to the redistribution of thermal energy and chemical substances across the ocean system. Volcanic island chains within Panthalassa formed through repeated eruptions at fixed points in the ocean floor. These islands were often arranged in sequences that recorded the movement of tectonic plates over stationary volcanic sources. As new islands formed, older ones changed position relative to the ocean floor and became subject to erosion and subsidence. The sedimentary record within Panthalassa contains evidence of long-term changes in ocean conditions. Layers of sediment reflect variations in volcanic activity, biological productivity, and chemical composition of seawater. These records provide information about the environmental state of the ocean during different intervals of geological time. Marine organisms in Panthalassa adapted to a wide range of environmental conditions. Some species inhabited shallow coastal waters, while others lived in open ocean regions or deep seafloor environments. Adaptations included variations in body structure, metabolic processes, and reproductive strategies that allowed survival in different parts of the ocean. The movement of nutrients through Panthalassa played a central role in sustaining marine ecosystems. Nutrient cycling involved the transfer of elements through biological activity, decomposition, and physical transport by ocean currents. These cycles maintain the availability of essential elements required for life throughout the ocean system. The interaction between Panthalassa and the atmosphere influenced global climate patterns during the time of Pangea. The ocean served as a major reservoir of heat and moisture, affecting atmospheric stability and the distribution of climatic conditions across the planet. Seasonal variations in ocean temperature contributed to changes in atmospheric circulation. Tectonic activity within Panthalassa also influenced seismic activity. Movements of the ocean floor generated energy that was released through earthquakes beneath the ocean. These events altered the structure of the seafloor and contributed to changes in underwater landscapes over time. The chemical exchange between Panthalassa and the atmosphere involved the movement of gases such as carbon compounds and oxygen. These exchanges occurred through diffusion at the ocean surface and through biological processes. The balance of these gases influenced both ocean chemistry and atmospheric composition. The long-term development of Panthalassa involved continuous interaction between geological, chemical, and biological systems. The ocean floor changed through ongoing tectonic processes, while the water column supported dynamic chemical and biological cycles. These interacting systems formed a continuously evolving marine environment. Subsurface processes within the ocean crust contributed to the formation of new rock and the recycling of older material. Magma rising from deeper layers of Earth created new crustal structures, while older sections of crust were transported into the interior through subduction processes. This cycle maintained the renewal of the ocean floor across Panthalassa. The distribution of marine habitats within Panthalassa depended on depth, temperature, light availability, and nutrient concentration. Different ecological zones formed across vertical and horizontal gradients within the ocean. Each zone supported distinct forms of marine life adapted to local conditions. The interface between the ocean and the seafloor in Panthalassa included environments where sediments interacted with biological activity. Microorganisms in these regions participated in chemical transformations that affected sediment composition and nutrient availability. These interactions contributed to long-term changes in ocean chemistry. Early signs of continental rifting and breakup refer to the first physical and geological changes that begin to appear inside a large landmass before it starts to separate into two or more different land areas. These early signs develop over a very long period of time and involve slow changes deep inside the Earth and on the surface of the land. They are connected to movements within the Earth's interior, especially within the mantle and the crust. The crust is the outer solid layer of the Earth, and it is broken into large sections that slowly move because of heat and pressure from below. When these forces begin to act strongly in one region of a continent, the land starts to weaken and stretch. One of the first early signs of continental rifting is the gradual stretching of the land. This stretching does not happen quickly. It begins with slow movement of rock layers inside the crust. The rocks begin to pull apart due to forces coming from deep inside the Earth. These forces are connected to rising heat from the mantle. As the heat rises, it creates movement in the material below the crust. This movement places tension on the rigid land above it. Over time, this tension causes the crust to become thinner in certain regions. As the crust becomes thinner, it begins to bend and deform. The surface of the land may begin to show long, narrow depressions. These depressions are areas where the ground has dropped slightly. Due to the stretching below, they form because the crust cannot maintain its original shape under continuous pulling forces. These depressions are often one of the earliest visible surface changes linked to rifting. At this stage, the land still remains continuous, but internal weakening is already in progress. Another early sign involves the formation of cracks in the crust. These cracks are called faults. Faults form when the rock layers break due to stress. The stress comes from the pulling motion acting on the land. When the rock breaks, it does not break evenly. One block of rock may move downward while another remains higher. This movement creates a stepped pattern in the ground surface. These fault structures are important indicators that the crust is undergoing structural change. As the rifting process continues, more faults begin to appear in the same region. These faults may follow a similar direction because they are influenced by the same forces. The repeated breaking of the crust causes the land to become more unstable. The surface may begin to show a series of parallel cracks and depressions. These features mark areas where the crust has been weakened and broken into segments. Deep below the surface, changes also begin to occur in the mantle. Hot material from deeper layers of the earth starts to move upward. This upward movement is caused by heat differences within the mantle. As the hot material rises, it pushes against the base of the crust. This adds more pressure to the already stretching land above. The rising material also causes the crust to become warmer in some regions. The increase in temperature affects the strength of the rocks, making them more flexible and easier to deform under stress. Magma may begin to form in areas where the mantle material becomes partially melted. This magma is molten rock that can move upward through cracks in the crust. When magma reaches higher levels within the crust, it can spread into existing fractures. This process increases the widening of cracks and supports further weakening of the land structure. In some cases, magma may remain trapped within the crust, forming large underground bodies of molten rock. Another early sign of continental rifting is the development of elongated valleys. These valleys form as blocks of crust slowly drop down between fault lines. The downward movement creates long, narrow depressions that follow the direction of the faults. These valleys are not formed by surface erosion, but by internal movement of the Earth's crust. The formation of these features marks a clear stage in the weakening of the continental structure. The crust in rifting regions often becomes uneven in thickness. Some parts remain relatively thick, while other parts become thinner due to stretching. The thinning process continues as the crust is pulled apart. This thinning allows deeper heat from the mantle to have a stronger effect on the surface layers. The interaction between heat and mechanical stress increases the rate of deformation in the affected region. Seismic activity begins to increase during the early stages of continental rifting. Small earthquakes occur as faults form and move. These earthquakes are caused by sudden shifts in rock blocks along fracture lines. The movement is usually not continuous but happens in small steps. Each movement releases energy stored in the rocks. The presence of frequent seismic activity is a clear indication that the crust is undergoing active deformation. Volcanic activity may also begin to appear in areas where rifting is developing. This activity is linked to the movement of magma from deeper layers of the Earth. As magma rises through cracks and weak zones, it can reach the surface and create volcanic eruptions. These eruptions may release lava, gases, and ash. The presence of volcanic activity shows that the crust has become permeable enough to allow material from deep within the Earth to escape. The surface of the land may also begin to show signs of heating. In some regions, hot springs and geothermal areas may form. These features occur when underground heat reaches close to the surface and warms groundwater. The heated water then rises and emerges at the surface. These thermal features are often associated with zones where the crust is thinning and becoming more fractured. As the rifting process continues, the central region of the affected area becomes more clearly defined. This central zone is where most of the stretching, faulting, and subsidence occur. The edges of this zone may remain relatively stable, while the middle region undergoes continuous deformation. The structure of the land becomes increasingly segmented, with blocks of crust moving independently in different directions. Sediment accumulation begins to occur in the low areas formed by rifting. These low areas collect materials that are transported by wind, water, and gravity. Over time, layers of sediment build up in the depressions. These sediments can include sand, clay, volcanic material, and organic remains. The accumulation of sediments helps preserve evidence of the rifting process in the geological record. Water systems may begin to respond to the changing landscape. Rivers and streams can change their direction due to the formation of new valleys and depressions. Water may flow into newly formed basins created by subsiding crust. Lakes may also begin to form in areas where the land has dropped significantly. These water bodies are directly influenced by the structural changes taking place in the crust. The stress field within the crust changes during early rifting. Stress refers to the distribution of force within rocks. As the crust is pulled apart, the direction and intensity of stress shift. This shift influences the orientation of faults and fractures. The alignment of these structures often reflects the direction of crustal stretching. The chemical composition of volcanic material in rifting regions may also show variation. Magma rising from deeper sources can carry different chemical elements, depending on its depth of origin. As it interacts with the crust, it may also change in composition. These chemical variations provide information about the processes occurring beneath the surface during rifting. The lithosphere, which includes the crust and the upper part of the mantle, becomes mechanically weaker during early rifting. This weakening is caused by both heating and physical stretching. As the lithosphere weakens, it becomes more prone to deformation. This allows faults and fractures to develop more easily across the affected region. In some areas, uplift of the land may occur before or during the early stages of rifting. This uplift is caused by the rising of hot mantle material beneath the crust. As the material rises, it pushes the crust upward in certain regions. This uplift can create elevated areas that later become part of the rift system when stretching continues. The distribution of rock types within the rifting region may also begin to change. Older rocks may become exposed due to faulting and erosion. Newer rocks may form from volcanic activity and sediment deposition. These changes reflect the ongoing transformation of the land as it responds to internal forces. Gas emissions may increase in areas where magma approaches the surface. Gases such as carbon dioxide and sulfur compounds can escape through fractures in the crust. These emissions are associated with volcanic and tectonic activity. The presence of gas release indicates that deep earth processes are actively influencing the surface environment. The boundaries of the rifting zone may become more clearly defined over time. These boundaries are marked by fault systems and zones of deformation. Within these boundaries, the crust experiences the most intense stretching and breaking. Outside these boundaries, the crust may remain relatively stable for a longer period. As time continues, the repeated action of faulting, stretching, and magma intrusion leads to a more organized rift structure. The central depression becomes more pronounced, and the surrounding areas adjust to the changes in stress and pressure. The landscape continues to evolve as internal forces reshape the structure of the crust. Pangea was a very large landmass that existed during a long period of Earth's past, when most of the Earth's land was joined into one connected system. The way land was arranged across this landmass followed a clear physical organization shaped by deep Earth movement over a very long span of geological time. The land was not scattered randomly. Instead, it formed a structured arrangement that included major regions of connected continental crust that were positioned in ways that reflected how the Earth's plates had moved and joined together through long processes. The arrangement of land across this supercontinent included areas that are now separate continents, and these areas were placed in positions that were different from their present-day locations. At the center of this land system, there was a broad interior region made up of continuous land that stretched over vast distances without interruption by large ocean basins. This interior region was not uniform in its surface conditions, but it remained a connected land surface where large geological formations extended over long distances. The arrangement of rocks, basins, and elevated regions followed patterns formed by earlier collisions and compressions of smaller land fragments. These fragments had come together gradually, and after joining, they formed larger blocks of continental crust that became part of the central interior of Pangea. The distribution of land also included two major large groupings of continental areas that were positioned in different parts of the supercontinent. One of these groupings is known as Laurasia. This landmass included regions that would later become parts of North America, Europe, and large parts of Asia. These regions were connected into one continuous land system. The placement of Laurasia formed a broad northern section of the global land arrangement. The internal structure of this region included ancient mountain belts, formed from earlier collisions of smaller land pieces. These mountain belts extended across large distances and influenced how rivers, basins, and sedimentary areas developed across the land. The other major grouping of continental land in Pangea was Gondwana. This region included what would later become South America, Africa, Antarctica, Australia, and the Indian subcontinent. These areas were joined into one continuous land system that occupied a large southern portion of the supercontinent. The distribution of land within Gondwana included a wide range of geological environments, from ancient stable crustal regions to areas that had been shaped by earlier tectonic activity. The structure of this landmass reflected long periods of crustal movement and accumulation of material from earlier geological eras. The position of Laurasia and Gondwana within Pangea was arranged in a way that created a broad continuous land connection between the northern and southern regions. These regions were connected through zones of crustal contact, where earlier oceanic areas had been closed by the movement of tectonic plates. The closure of these oceanic areas resulted in the joining of land fragments into continuous continental surfaces. The arrangement of land in these zones included folded rock formations, thickened crust, and large structural belts that extended across long distances. Within the interior of Pangea, there were also smaller crustal blocks and microcontinental fragments that had been incorporated into the larger land system. These fragments were once separate land areas that had moved over long periods and eventually became attached to larger continental masses. Their presence contributed to the complexity of the internal arrangement of land. These smaller blocks were not isolated in appearance because they were fully integrated into the surrounding continental crust. Their boundaries were often marked by zones of deformation where rocks had been compressed, folded, and altered due to tectonic forces. The distribution of land across Pangea also included extensive mountain systems that were formed during the time when different continental blocks came together. These mountain systems were distributed along the zones where landmasses had collided. The rocks within these systems showed evidence of intense pressure and temperature conditions that occurred during the process of continental joining. These mountain belts extended across long regions of the supercontinent and played a role in shaping the arrangement of rivers, sediment accumulation areas, and erosion patterns across the land surface. Large inland regions existed within the central areas of Pangea. These inland regions were far from the edges of the landmass and were influenced by their distance from oceanic water bodies. The arrangement of land in these interior zones included broad basins where sediments collected over time. These basins formed through gradual sinking of the crust in response to weight distribution and tectonic adjustments. The sediment layers within these basins accumulated from surrounding elevated regions and from erosion processes that moved material across the land surface. The outer edges of Pangea were shaped by long coastal zones where land met the surrounding ocean system. These coastal zones were not uniform in structure. They included areas of sediment accumulation, volcanic activity, and tectonic interaction. The arrangement of land along these edges reflected the interaction between continental crust and oceanic crust. Subduction zones existed in certain areas where oceanic crust moved beneath continental crust, leading to the formation of volcanic arcs and mountain chains along parts of the margin. The northern part of Pangea, where Laurasia was located, included a wide distribution of ancient rock formations that had formed during earlier geological periods. These rock formations included stable continental shields and cratonic regions that had remained relatively unchanged over long spans of time. These stable regions formed the foundation of the northern land distribution. Around these stable cores, younger geological formations were added through processes of sedimentation, volcanic activity, and tectonic movement. In the southern part of Pangea, within Gondwana, the distribution of land included large shield areas that formed the core of several present-day continents. These shield areas consisted of very old crystalline rocks that had formed deep within the Earth's crust. Over time, these areas were exposed at the surface through erosion and uplift. Surrounding these shields were sedimentary basins and folded mountain belts that recorded the history of earlier geological activity before the formation of the supercontinent. The arrangement of land also included long structural zones that extended through both northern and southern regions of Pangea. These structural zones were formed by the movement of tectonic plates that caused deformation of the crust over extended periods. Within these zones, rocks were folded and faulted, creating complex patterns of geological structure. These zones often acted as boundaries between different crustal blocks and influenced the distribution of geological features across the supercontinent. Rivers within Pangea followed pathways that were shaped by the arrangement of land. These river systems moved across interior basins and through low-lying regions of the crust. The distribution of drainage systems reflected the positions of elevated regions and structural basins. Water movement across the land surface transported sediment from high areas to low areas, contributing to the development of thick sedimentary sequences in certain regions. The distribution of volcanic regions across Pangea was concentrated mainly along tectonically active margins. These volcanic regions formed where the movement of Earth's plates created conditions for magma to rise toward the surface. The placement of volcanic systems was closely connected to the arrangement of subduction zones and crustal boundaries. These volcanic areas contributed new material to the crust and influenced the formation of mountain belts and surface structures. Large desert-like interior regions existed in parts of Pangea where the land was far from oceanic moisture sources. The distribution of land created conditions where atmospheric moisture did not easily reach certain inland areas. These regions experienced limited precipitation, and surface processes in these areas were dominated by wind-driven movement of sediment and slow weathering of exposed rock surfaces. The arrangement of landmasses influenced how atmospheric circulation patterns moved across the supercontinent. The internal arrangement of crustal blocks within Pangea included zones of thickened crust where multiple land fragments had merged. These zones were characterized by deep crustal roots that extended downward into the earth. The distribution of these thickened regions reflected earlier collision events that brought separate landmasses together. Over time, these regions stabilized and became part of the long-lasting structure of the supercontinent. The boundaries between Laurasia and Gondwana were not simple straight divisions. Instead, they consisted of complex zones where multiple smaller terrains and microcontinents had been incorporated into the larger system. These zones contained mixed geological features, including folded rocks, metamorphic belts, and sedimentary sequences that recorded different stages of geological development. The arrangement of these boundary regions reflected long-term tectonic interaction between different crustal blocks. The distribution of mineral resources across Pangea was influenced by the geological processes that formed and modified the crust. Different regions contained different types of mineral deposits depending on their geological history. Areas that had experienced volcanic activity contained deposits formed from magma-related processes. Regions that had undergone sedimentation contained deposits formed from the accumulation and chemical transformation of materials over time. These distributions were closely tied to the structural arrangement of the land. The interior stability of large portions of Pangea allowed for long periods of surface development without major disruption in certain regions. Stable crustal areas supported the formation of extensive sedimentary basins and preserved geological records of long-term environmental conditions. These stable regions were part of both Laurasia and Gondwana, where they formed the foundation of the land distribution. The arrangement of land across Pangea also included zones where crustal material was recycled into deeper parts of the earth. These zones were located along the edges of the landmass where oceanic crust interacted with continental crust. Material from these regions was transformed through heat and pressure and contributed to the formation of new geological structures. The distribution of these processes influenced the overall structure of the supercontinent. The surface of Pangea contained a wide variety of elevation levels, from high mountain regions to low basins and plains. These variations in elevation were directly related to the arrangement of tectonic structures beneath the surface. Areas with thickened crust formed elevated regions, while areas with thinner crust formed lower basins. This distribution created a varied landscape across the supercontinent, with different geological conditions present in different regions. The movement of sediment across Pangea was controlled by the arrangement of landmasses and the positions of elevated and low regions. Sediment was transported from high areas through erosion processes and deposited in lower regions where basins existed. Over long periods, this led to the formation of thick sedimentary layers that recorded the history of surface processes across the supercontinent. The distribution of crustal stress across Pangea was not uniform. Some regions experienced higher levels of tectonic stress due to ongoing interactions between different crustal blocks. These stresses led to the formation of faults and folds in the rock layers. Other regions remained more stable, allowing older geological structures to remain preserved without significant deformation. The arrangement of land across Pangea continued to evolve slowly over time due to ongoing internal Earth processes. Even after the main formation of the supercontinent, internal adjustments in the crust continued to modify the distribution of geological features. These adjustments included gradual uplift, subsidence, and lateral movement of crustal blocks within the larger land system. The formation of the Tethys Ocean during the separation of large land areas on Earth happened through long and slow movements inside the Earth that changed the shape of the surface over a very long time. This process took place when large connected landmasses that once formed a single giant land area began to break apart and move away from each other. The space that opened between these moving landmasses slowly filled with ocean water, and this growing body of water became known as the Tethys Ocean. The development of this ocean was not a single event, but a long sequence of changes in the Earth's crust, the opening of cracks, the sinking of parts of the crust, and the steady inflow of seawater over millions of years. The Earth's outer layer is made of solid pieces that are not fixed in one place. These pieces are part of a larger system that allows slow movement over long periods of time. Deep inside the Earth, heat causes slow movement of materials. This movement creates forces that act on the outer solid layer. When these forces stretch parts of the crust, the land begins to thin and weaken. Over very long periods, this stretching leads to breaking. When breaking begins, long cracks form. These cracks may continue to grow, and when they widen, they create space that can later become filled with water from nearby oceans. During the time when the large connected landmass existed, there was a stage when internal forces inside the Earth started to pull parts of this landmass in different directions. This landmass was made up of many smaller continents joined together. The stress inside the Earth increased in certain zones where the crust was weaker. These weak zones became the first places where breaking started. The breaking process began slowly, and it continued for a very long time without sudden changes on the surface. As the stretching continued, the land began to sink in certain areas. This sinking created long and narrow low regions. These low regions became pathways where seawater could enter. At first, these areas were not fully filled with water. They were partly dry land and partly shallow water. Over time, more water entered as the openings became wider and deeper. The gradual filling of these spaces marked the early stage of ocean formation. The separation of land areas that led to the formation of the Tethys Ocean began during a time when the Earth's surface was arranged in a very different pattern from today. This time began more than 200 million years ago. At that stage, large connected land areas were still present. The internal heat of the Earth continued to move material beneath the surface, and this movement slowly pushed and pulled the crust in different directions. The stress created by this movement caused fractures to form in specific regions. These fractures slowly developed into long rift zones. A rift zone is a long area where the crust begins to break and move apart. In the early stage of the formation of the Tethys Ocean, such rift zones appeared between major parts of the large landmass. These rift zones did not open quickly. They expanded slowly over millions of years. The crust in these zones became thinner as it was pulled apart. The thinning crust became weaker and more likely to sink. When the crust sank, it formed low basins that were below the surrounding land level. Water from nearby seas began to enter these basins. At first, the water was shallow and limited to narrow channels. Over time, as the rift zones widened, the water spread further. The inflow of seawater was not constant, but occurred in stages, depending on the level of opening in the crust. Each stage of opening allowed more water to enter and remain trapped in the newly formed basins. As the process continued, the separation between landmasses became more pronounced. One side of the separating land moved in one direction, while the other side moved in another direction. This movement increased the size of the opening between them. The opening became a long and continuous marine space. This marine space later developed into the early form of the Tethys Ocean. The formation of this ocean was closely linked to the movement of large crustal plates. These plates are massive sections of the Earth's outer shell that move slowly over time. The movement of these plates is driven by heat from deep inside the Earth. This heat causes slow circulation patterns in the material beneath the crust. These patterns push and pull the plates, causing them to move apart or come together. When plates move apart, new crust can form in the opening area. This happens when molten material rises from deeper regions and cools at the surface. However, during the early formation of the Tethys Ocean, the main focus was on the separation process. The pulling apart of plates created space that allowed ocean water to enter and spread. The areas where the crust began to break were not uniform. Some regions broke earlier than others. Some regions stretched more slowly. The variation in movement created a complex shape for the developing ocean. Narrow seaways formed in some places, while wider basins formed in others. These different shapes gradually connected to form a larger, continuous water body. The surrounding land areas also changed during this process. As the crust stretched and sank in some regions, it rose in others. This movement created high and low regions across the surface. The high regions remained above sea level, while the low regions became filled with water. The balance between rising and sinking land shaped the outline of the growing ocean. The early Tethys Ocean developed in a zone between northern and southern land areas that were slowly moving apart. The northern land areas later became parts of continents in the northern hemisphere, while the southern land areas were part of a large southern landmass. The separation between these regions widened gradually. The widening created a long marine corridor that extended over very large distances. Sediments began to collect at the bottom of the newly formed ocean areas. These sediments came from erosion of nearby land. Rain, wind, and flowing water broke down rocks on land and carried small particles into rivers. Rivers then carried these particles into the ocean basins. Over time, these sediments accumulated and formed layers on the ocean floor. These layers recorded the changes taking place during the formation of the ocean. The chemical composition of the seawater also changed, as more water entered the basins and interacted with surrounding rocks. Minerals dissolved from rocks and entered the water. These minerals affected the properties of the seawater. The interaction between water and rocks continued throughout the development of the ocean. Volcanic activity also played a role in the formation of the ocean. In regions where the crust was thinning, molten material from below sometimes reached the surface. This volcanic activity added new material to the ocean floor. It also released gases that mixed with the atmosphere and seawater. The presence of volcanic activity helped shape the structure of the developing ocean basins. As time passed, the separation between the landmasses continued to increase. The movement was steady and occurred over millions of years. The ocean basin became wider and deeper in many regions. The Tethys Ocean became a long and continuous body of water, separating major land areas. The boundaries of the ocean changed gradually as the surrounding plates continued to move. The shape of the ocean was influenced by the direction of plate movement. Some parts of the crust moved more directly apart, while others moved in slightly different directions. These variations created bends and curves in the ocean's outline. The complexity of the movement resulted in a varied structure of basins and channels within the ocean system. The water within the ocean came from existing seas that expanded into the newly formed basins. Additional water also came from precipitation over long periods of time. As the basins deepened, they were able to hold more water, and the ocean gradually expanded in volume. The process of filling and deepening continued without interruption for long geological periods. The climate conditions during the time of formation influenced the rate of sedimentation and water movement. Warm conditions in some regions led to increased evaporation and precipitation cycles, which affected water circulation. These changes influenced how sediments were transported and deposited in different parts of the ocean basin. The development of the Tethys Ocean also involved changes in the structure of the ocean floor. As new crust formed in some areas and older crust moved away, the shape of the ocean floor became more complex. Ridges and basins formed due to differences in crustal movement. These features guided the flow of water and the deposition of sediments. The continuing movement of plates ensured that the ocean did not remain static. Even after the initial formation, the ocean continued to change shape. Some areas widened further while others narrowed due to shifting crustal boundaries. The overall system remained active with continuous geological processes affecting its structure. The interaction between land, water, and crustal movement created a dynamic environment. Rivers continued to supply sediments, volcanic regions continued to release material, and plate movement continued to reshape the basin. These combined processes maintained the evolving nature of the ocean over very long time spans. The separation that formed the Tethys Ocean also influenced the arrangement of surrounding landmasses. As the ocean widened, continents moved further apart, creating distinct land regions on either side of the ocean. These land regions developed their own geological features due to continued tectonic activity. The growth of the ocean basin also influenced ocean circulation patterns. Water movement within the basin changed as the shape of the ocean evolved. Currents developed in response to the geometry of the basin and the inflow of water from surrounding regions. These movements contributed to the distribution of sediments and dissolved materials within the ocean. The process of ocean formation did not occur evenly across all regions. Some areas experienced rapid widening while others changed more slowly. This uneven development created a complex pattern of marine and shallow water environments. These environments shifted over time as the ocean continued to expand. The early stages of the Tethys Ocean were marked by transitions from land to shallow water environments, and then to deeper marine conditions. These transitions occurred gradually as the crust continued to separate. The progressive sinking of the crust allowed deeper water to accumulate in certain areas. The long duration of these processes meant that the ocean had enough time to develop a stable structure in some regions while remaining active in others. The balance between stability and ongoing change defined the evolving nature of the ocean basin. Sediment layers continued to build up over time, creating a record of the environmental conditions during the formation of the ocean. These layers contained information about erosion, volcanic activity, and water movement. The accumulation of sediments played a significant role in shaping the final structure of the ocean floor. The formation of the Tethys Ocean was part of a larger pattern of continental movement that affected the entire surface of the Earth. As one ocean formed, other regions experienced similar processes of rifting and separation. The movement of crustal plates continued across different parts of the globe, leading to changes in the distribution of land and sea. Throughout the long process of formation, the Tethys Ocean remained a developing marine system shaped by continuous geological forces. The movement of the Earth's crust, the inflow of seawater, the deposition of sediments, and the activity of volcanic regions all contributed to its development. The ocean expanded gradually as the separation of landmasses continued over extended geological time, with the structure of the basin continuously adjusting to ongoing changes in the Earth's surface. The drift of continents toward their present-day positions is a long and continuous process that took place over an extremely large span of Earth's history. It is part of the movement of the Earth's outer layer, which is made of many large and small pieces of solid rock. These pieces are called tectonic plates, and they slowly move across the surface of the planet over time. The idea that continents move is explained by the concept of plate tectonics, which describes how Earth's surface is not fixed, but is always slowly changing. The movement of continents did not happen in a single moment or in a short period. It happened gradually over hundreds of millions of years. At earlier times in Earth's history, the continents were not arranged in the way they are today. They were joined together in large landmasses, and over time, these large landmasses broke apart and slowly moved to different positions on the globe. The motion is still happening today, even though it is extremely slow and not visible to human sight without careful measurement. The Earth's outer layer is divided into several major plates. These plates are very large sections of solid rock that float on a softer layer beneath them. The movement of these plates is driven by heat inside the Earth. The heat comes from deep within the planet and causes slow movement in the material beneath the crust. This movement causes the plates on top to shift in different directions. When continents are attached to these plates, they move along with them. Over long periods of time, this movement changes the positions of the continents. The drift of continents began after large landmasses broke apart. One of the most important stages in Earth's history was when a large supercontinent existed. This supercontinent contained most of the Earth's land in one connected mass. Over time, this supercontinent began to break into separate pieces. These pieces became the early forms of the continents we know today. As the plates moved, the pieces slowly drifted away from each other. At the beginning of this process, the land was joined in a way that made travel across land possible between regions that are now far apart. As the plates moved, new ocean spaces formed between the separating landmasses. These ocean spaces grew wider as time passed. The movement was not steady in a single direction. For all landmasses, each plate moved in its own direction based on the forces acting on it. The movement of continents is very slow. It happens at a rate that is usually measured in centimeters per year. Even though this rate is very small, it becomes very large when measured over millions of years. Over such long periods, continents can travel thousands of kilometers from their original positions. This slow motion is why the continents today are in very different places compared to their earlier positions. As the continents moved, the shapes of the Earth's surface changed. New oceans formed and existing oceans changed in size. Some ocean areas became wider as continents moved apart. Other ocean areas became smaller when continents moved closer together, or when ocean floor was pushed downward under continental plates. This process of movement and change continues today. The edges of tectonic plates are very important in understanding continental drift. At some edges, plates move away from each other. At other edges, they move toward each other. At other edges, they slide past one another. When plates move away from each other, new crust is formed. This process happens at places where molten material rises from beneath the Earth's surface and cools to form new rock. This new rock pushes the plates apart and allows continents to slowly move away from each other. When plates move toward each other, one plate may move under another plate. This process is called subduction. In these areas, parts of the Earth's crust are pushed down into deeper layers. This movement can lead to the formation of mountains and other large surface features. When continents move into these regions, their shapes can be changed by the forces involved in the collision and movement. The drifting of continents toward their present positions also involved changes in climate and environment across the Earth. As continents moved into new positions, they experienced different temperatures, rainfall patterns, and environmental conditions. These changes happened slowly and continuously as the continents moved across different parts of the planet. The movement of continents also affected the distribution of living things across the Earth. As land masses separated, populations of organisms became isolated from each other. Over long periods, these separated populations developed differently due to their isolation and different environmental conditions. This process happened gradually as the continents continued to move. The internal structure of the Earth plays an important role in continental movement. Beneath the crust is a layer of material that is hot and partially flexible. This layer allows the rigid plates above it to move slowly. The movement is not smooth in a simple direction, but happens in different directions depending on forces acting within the Earth. These forces include the movement of heat from deep inside the planet toward the surface. Heat inside the Earth moves in circular patterns. Hot material rises and cooler material sinks. This movement creates slow circulation patterns that help push and pull the tectonic plates above. As a result, continents attached to these plates are carried along in different directions over time. The breaking apart of earlier landmasses happened in stages. First, cracks formed in the large land areas. These cracks slowly grew larger as the plates continued to move. Over time, the cracks became deep valleys and then widened into ocean basins. Water filled these spaces, forming new seas and oceans between separating landmasses. As continents drifted, their edges changed shape due to erosion, sediment deposition, and tectonic activity. Mountain ranges formed in some areas where plates collided. In other areas, flat plains formed where sediment accumulated over long periods. These surface changes happened while the continents were moving, shaping the landforms that exist today. The drifting process also influenced volcanic activity. In some regions where plates moved apart, molten material rose to the surface and created volcanic features. In other regions where plates moved together, melting of crustal material led to volcanic activity. These processes added new rock to the Earth's surface and changed the shape of continents over time. The movement of continents also caused earthquakes. As plates moved, stress built up in the rocks at their edges. When this stress was released suddenly, it caused shaking of the ground. These events happened repeatedly over Earth's history and continue to happen today in many regions of the world. The direction of continental drift was not the same for all continents. Each continent followed its own path based on the direction of the plate it was attached to. Some continents moved toward the north, others toward the south, and others in different directions. These movements gradually created the current arrangement of landmasses on Earth. As continents moved, ocean floors also changed. New ocean floor was created in some regions, while older ocean floor was destroyed in others. This balance between creation and destruction helped maintain the movement of plates and continents over long periods of time. The separation of continents also led to the formation of large ocean basins. These basins filled with water over time and became the large oceans that exist today. As the continents continued to drift, the size and shape of these oceans changed slowly. The motion of continents is still occurring today. Measurements using modern technology show that continents continue to move in different directions. Even though the movement is very slow, it can be detected using precise instruments. This ongoing movement is part of the same process that has been active for hundreds of millions of years. The edges of continents are often active regions where geological changes are still happening. In these areas, mountains can still rise, oceans can still widen or shrink, and earthquakes can still occur. These changes are part of the continuing movement of tectonic plates. Over time, the continents reach positions that are closer to their present arrangement. However, even in the present time, the arrangement is not fixed. The continents continue to move, and the shapes of oceans and landmasses continue to change very slowly. The slow drift of continents is connected to the overall structure and behavior of the Earth. The planet is not static, but is always undergoing internal movement that affects its surface. The crust is broken into pieces that move independently, and this movement shapes the geography of the Earth. As continents moved into their current positions, they passed through different climate zones. Some continents moved from warmer regions to colder regions, while others moved in the opposite direction. These changes affected the physical conditions on the land, including the formation of ice in some regions and dry conditions in others. The movement also influenced sea levels in different areas. As continents changed position, the shape of ocean basins changed, which affected how water was distributed across the Earth's surface. This led to changes in coastlines and shallow sea regions. The drifting process also influenced the formation of natural resources. As continents moved and geological processes occurred, minerals and other materials formed in different regions. These materials became distributed in patterns that reflect the movement of the Earth's crust over time. The process of continental movement is ongoing and continuous. It does not stop, and it does not move in sudden, large steps. Instead, it happens slowly and steadily over time. The forces driving it come from deep within the Earth, and these forces have been active for a very long time. The present positions of continents are the result of this long movement process. Each continent has followed a path shaped by the motion of the tectonic plate beneath it. These paths have been influenced by interactions with other plates, internal Earth forces, and surface changes. The drifting of continents towards their current positions is part of a larger system of Earth dynamics. This system includes the movement of heat, the formation of rock, the recycling of crust, and the continuous reshaping of the planet's surface. All these processes work together over long periods of time. The separation and movement of continents also created new boundaries between land and sea. These boundaries changed over time as continents moved. Some coastlines formed gradually as land moved away from other land. Other coastlines changed as land was pushed upward or downward due to tectonic forces. The movement of continents also affected river systems. As land masses shifted, rivers changed their paths.